Gentlemen, welcome to today's conversation on parts count and reliability predictions. So just to show, sorry, my chat window's disappeared. So, all right, so I can't easily see everyone right now in terms of who's in and who's not. But Fred, how many people we got today?
It looked like registration was 66.
Right, that's cool. So what we're going to talk about today is reliability and parts count prediction. So this is one of the biggest issues we have in the world of reliability, because we're lazy by nature. We really are. Let's not pretend we're not. It's an evolutionary sort of adaptation to how we live our lives. And when it comes to being lazy, especially if we don't really want to take reliability seriously, there's this thing called reliability and parts count prediction, which can really, really be very helpful. In terms of, when I say helpful in that we get numbers onto a piece of paper that potentially make the issue or the problem that our boss is asking us go away. So before we talk about reliability and parts count prediction, I want to talk about us, the mean or essentially how tall human beings are. Specifically, think about the average or mean height of a person. And when I say average or mean height, we're talking about 165 centimeters or 5'5". That's the mean or average height of a person. And why is that important? Well, let's think about if you're charged with making a doorway in a house, you need to make your doorway tall enough or high enough for someone to be able to walk through it. And when I say walk through it, here is our doorway. So when it comes to our doorway, how tall does our doorway need to be? Now, a really simple way of looking at our doorway is say, well, let's make it the mean or average height, because we don't want to have our doorway too tall. If we make our doorway too tall, it affects the ceiling height. It affects so many other things. So how do we get the perfect doorway height? And when I say perfect, we want to be able to have people walk through the doorway. I'm going to use this as an analogy for reliability. So if we start with the mean or average human height, which we know is 165 centimeters or 5'5", then hopefully that means someone should be able to walk through said doorway. And here we have a person who is happily walking through our doorway. But that's not always the case, as we know, because not everyone's the same height. So the problem with having the mean height or using the average mean or average height of a human being for a doorway is that someone who is a little bit taller is going to have a bad day. And I need to apologize. We're going to have a couple of synchronizing issues with Microsoft, which will make Fred very happy. So we've got some blue numbers which might randomly appear in the top left-hand corner of my webinar, and it really shouldn't. So just brace yourselves for if you're cool with amateurism, then this is a sort of webinar for you. So we can see that even if we have the mean or average height and use that for the doorway, some people will still bang their heads. Around about half of people will bang their heads as they move through this doorway because about half of all people are a little bit taller than the average or mean height. So what does that mean? Well, if we're going to have a doorway, well, we need to make it a little bit bigger than the mean or average height. So let's look at this in a little bit more detail. If we look at the distribution or spread of human heights, we can see something really interesting. We can see the female height. You can see that red bell curve on the right and that blue bell curve. They're the distributions of both male and female human heights. And you can see that the height of the doorway sort of goes between the middle of them. So let's just say we're going to now look at this and say, you know, we need to allow most of the people that we're going to come across pass through the doorway. But it's not just female or male. We need to make sure we get the right subpopulation or population considered. You can see the combined height distribution, this grey bell-shaped curve. It's not quite bell-shaped curve, but it's a bell-like curve. That's a combined distribution of both male and female heights. And of course, a male and a female is equally likely to pass through our door. So perhaps our doorway is too short. Not perhaps, it clearly is. It clearly is too short because that shaded area or hatched area in that grey bell curve represents the percentage or fraction of people who are going to experience a head bump. So we need to make our doorway a little bit taller. So let's just say we make it that much taller. And it's great now because we have the distribution of combined human heights. And we can see that based on that distribution, the area beneath that curve that is above that red line is now very small. It's in fact less than 1% of the total area beneath that curve. So that means we are perhaps good to go when it comes to the height of our doorway. It's now a little bit higher than the mean, and that usually has to be the case for obvious reasons. So now we have the right doorway height. So we're good to go, perhaps. But let's just examine another scenario. And the other scenario is, well, unfortunately, this is the doorway at the practice facility for a professional basketball team. And why is that a problem? Well, you can see that the distribution of professional basketball heights, and that is a true distribution, is a little bit higher than the distributions associated with the male and female, typical male and female heights across the world. Now, here we have another scenario where we have this man who is from Timor-Leste. And if anyone who knows anything about Timor-Leste, that's just off the northwest coast of Australia. It is a small island nation, which also has the title or a distinction of being the shortest nation in the world. So we don't want to make our doorway too high because if we do, we lose money. And if we don't make our doorway too high, well, too many people bang their head. And so when it comes to working out how tall your doorway needs to be, it's not just simply finding a single number, finding the mean. There's a whole story behind what is essentially a random variable. And when I say random variable, the human height is a height of a human being, I should say, is a random variable. So as a preamble to what we're going to be talking about today, I want you to continually think about how tall the doorway should be in your world, in your space, because it's largely analogous to what we're going to be talking about today in the world of reliability and parts count predictions, which is a very special type of reliability engineering. So if you have or know something about the average of a random variable, the main takeaway so far is you really can't conclude with a ton of certainty how long or how big something should be, where that metric is going to have to somehow account for the most things or a significant majority of things or minimize the frequency of negative outcomes. And that's what the world of reliability is. We're trying to essentially build doorways in our systems, in our processes, in our products, where we minimize the likelihood of people banging their heads or our products failing. So how tall should your doorway be? Not based on the mean of the people around or across the world. How tall should the doorway be for your people? Not anybody else's people, your people. And that means you need to go well and truly beyond not only a single number for every single possible person in the world, you need to go beyond a single number for your own people and understand the spread of things, a la reliability engineering. So let's move away from doorways towards products and systems. Now, we are often in the business, if you're listening to this webinar, you're probably here because you need to make something reliable. Cool. And you might often come across a scenario where you're early in developmental, in the production process or design. So you need to have some sort of idea about how reliable your thing might be. And of course, that is where the world of reliability and parts count prediction come into play. There's a huge industry behind getting these numbers that allegedly give you some idea of reliability performance early on. So let's just say that the product you're responsible for is, ever so slowly about to come up on the screen, a milling machine just like this. So this is your next milling machine. Let's just say your organization is responsible for the design of the next generation of milling machines. You're a milling machine manufacturer. So when you are coming to terms with your milling machine, yeah, you're going to need to have some idea of its reliability performance for a huge range of decisions. Also, it could be down to something as simple as working out, is it feasible? Is this subsystem or this component feasible? And one way of understanding that is to understand how it's likely going to fail. So if you've heard of FAMICAs, where you have to have failure rates, that's a very well-known activity where we often try very early on to get estimates of how often our components are going to fail. And then that can help ideally prioritize our effort. Or maybe we'll go one step further where you are actually going to need or be asked to model the reliability of your system. And so if you have a fault tree, for example, like this, which is a system reliability model, then we can work out, for example, the role of one of those basic events, which is a component failure, influencing system reliability, specifically my ball bearing, which is one of my go-to components in the world of my webinars on Ascendo. So if we look at this computer here, it has the ball bearing right in the middle of it. Why am I showing you this image right now? Well, if you are so inclined to understand the reliability or try and predict the reliability of your ball bearing early in the design process, because as we know, milling machines have rotating shafts that they carry an immense amount of torque. So you might want to search the internet or search the body of literature out there to try and understand how reliable your initial concept of a ball bearing is going to be. And so if you go to certain web searches and things like that, you might come across these sorts of tables where we have a list of generic items. You can see on the left, sorry, it's been faded out, where on the right-hand side, we have, oh, good Lord, we have these nominal failure rates for different types of components and different types of products and assemblies. And so now you have on the web, I should say, alleged so-called failure rates, which might help us understand how our ball bearing is going to fail in the real world. Now, these tables, which are often referred to as reliability prediction tables or parts count tables, they usually just simply have these numbers, which represent the predicted number of failures per million hours. And in some cases where hours aren't the right metric, they have the letter C after those numbers to represent, this is not per million hours, this is per million cycles. And so for ball bearings in particular, we don't measure usage in terms of hours, we tend to measure usage in terms of cycles. So you see there's a number next to ball bearings, which has the letter C next to it, which tells us that this table suggesting our ball bearings should fail about 1.9056 times every million cycles. So this is sort of where many organizations first start to try and find an understanding of the reliability performance of their emerging components and products. But many can actually take you a little bit deeper. So for example, on these tables, we can go to certain places, certain resources, and they can show you exactly where they get the data for this alleged failure rate of 1.9055C, i.e. 1.905 failures per million cycles. And you can see here we have 6 rows with numbers, and each row corresponds with a single source of data that the organization behind this particular table used to get that number of 1.9055C. Now you can see that some rows just simply have a point estimate, like 0.0245. Other rows go a little bit more detail where they say, no, the data source for this one was based on some organization, some entity which experienced 788,022 cycles for its bearing and experienced 0 failures. So the failure rate estimate from this organization is less than 0.12697. And you can see as we go down the list, you have all these different numbers which show to an extent how the organization got these numbers. So one takeaway is what we are clearly not talking about huge amounts of data here. So I am scrubbing data essentially to keep those sources anonymous. But these are indicative numbers I've changed ever so slightly from relatively well-known sources out there that we often go to try and find these failure rates for these components that are going to be part of our amazing new product, our amazing new milling machine, or whatever it is we're designing from scratch. So if we're not talking about a huge amount of data, which we're not, the reality is you need to be very aware of what this data means for these so-called well-researched numbers from the internet, from the web, wherever you're getting these numbers from. And it's not necessarily a criticism, it's just a fact. Now, before we go on and say, hey, that's shocking, we should never have should never publish failure rate estimates for things like ball bearings without a ton of information that's been double peer reviewed and researched and everything else. So before anyone jumps on that bandwagon and say, well, they really should use a huge amount of data before they publish these failure rates, the question I'd ask you is, does your organization happily publish all the times your components fail? The answer is no. Let's not pretend it's not. And so most organizations don't release failure data. So we only have a really small amount of data, and it's often very dated. But if you want to do your due diligence, you should go to those sources where you have failure rate estimates where they show you where the numbers come from. So we're not talking about huge amounts of data, but this is sort of from these tables you can find online, essentially as good as it gets very early on in your design process from one point of view. Now, if our failure rate for our ball bearing is allegedly 1.9055 failures per million cycles, now we've got a number that we can plug into our system reliability model or our FMECA to make amazing decisions. Well, let's hold on to that thought for 1 second, because with ball bearings, we know how ball bearings work. We also know how they fail. So here's my good old random hand of failure. For those veterans, you know that this is the way I characterize the different factors which influence a random process like failure. And yes, failure is a random process. And the idea is that this random hand of failure, which represents all these factors, is based on, for the case of ball bearings, factors like particle contamination in the lubricant. And that sort of pie slice on the right just represents the extent to which particle contamination drives ball bearing failure. You can see that's quite a large slice. So one of the biggest issues that drives ball bearings failure is particle contaminations in the lubricants. The next most significant factor is misalignment. So this, again, these two things, these first two big factors aren't actually issues with the ball bearings themselves. They're issues with the organization that uses those ball bearings. So for example, if the ball bearing is used in an environment where it's very dirty or the shaft isn't properly aligned, that's not really an issue or problem or fault of the manufacturer. That's an issue of the user, not the end user of the machine, of the product, I should say. It's the overall client or not customer, the client who's building or using these bearings to make an amazing product, such as a milling machine. So let's keep going. What else drives ball bearing failure? Oh, disassembly damage. That is preventive maintenance. So that's another issue that is not necessarily a fault or can be attributed to the ball bearing manufacturer. It's the operator of the ball bearing. What else? Insufficient lubrication. Again, the next most important factor is the operator. Do they provide enough lubricant for the ball bearing? What's the next one? Humidity, which causes corrosion. That's an environmental factor. Now, of course, you can buy ball bearings which are more or less able to tolerate humid environments, and you obviously should. But at the end of the day, if you select a ball bearing which is not rated to the humidity of your operating environment and it rusts out, again, that's not on the manufacturer, that's on you. So what's another factor? Excessive loads, design issues, again, not associated with the manufacturer of the ball bearing, it's associated with the operator or the design team. And what's the next one? The next one is manufacturing defects. So finally, we've got to the smallest factor, and these factors are based on research into ball bearing failures over the year. It appears as if the most prevalent, the factor which drives time to failure the least is manufacturing quality. So why am I doing this? Well, if you look at all these factors right next to each other, the reality is if you are the operator or you're the design team, the other factors which drive ball bearing failure are you, what you choose to do with the ball bearing, how you choose to use the ball bearing, the environment within which you choose to employ that ball bearing, any discrepancies between said environment and the ball bearing you select, et cetera, et cetera, et cetera, et cetera. So a good chunk of ball bearing reliability is on how you use that ball bearing, how you maintain it, how you look after it, how you install it, how you align it, so on and so forth. Now, why am I saying this? Well, clearly, there's a lot more at play to reliability than just getting something off the shelf. So here are the times to failure of a good chunk of ball bearings. These blue dots, each one of them represents the times to failure of a ball bearing based on all those factors combining and interplaying and just otherwise ruining the life of your ball bearing. Now, we know ball bearings will fail. They're going to fail. That's not a surprise. And so because we're good reliability engineers and there's a lot of the body of knowledge on ball bearing failure is relatively substantial, we actually have a really good understanding of how ball bearings fail. And their statistical signature looks like this. You have this curve which has a peak and this right tail. You can sort of see how it's held steady on the left-hand side and it's pushed across to the right or pulled out or stretched to the right, as you can see. So why is this important? Well, we need to understand this statistical signature to learn how to love and respect and take care of our ball bearing. So this curve here, this probability density curve, is something that if we're serious about the reliability of our ball bearing, we need to understand intimately because, as we're about to see, the shape of this curve drives so many other really important things. Like, let's think about the mean, for example, the mean cycles to failure. Now, all the mean is for those newbies here is it's essentially the balance point of that curve you can see on the screen right now, right there. Now, that orange curve, probability density curve, it describes the likelihood of our cycles to failure being a particular value. So our curve is higher where those data points are denser. And this is how our brains like to visualize uncertainty. The higher the density, the more tightly packed those times to failure or cycles to failure are at that point. Now you can see that our balance point, it represents a typical value. It's one way of characterizing a typical number of cycles to failure for our ball bearing, but that's all it is. It's the balance point. We often treat the mean time to failure or mean cycles to failure as a physical metric. It's not. And we're going to really understand why by the end of this conversation. So that's the mean, that balance point. We also call it, as I said, we call it the mean time between failure or mean time to failure for something that's not getting replaced. We often represent it with the Greek lowercase letter mu. That's all the mean is. And we're going to reference the mean a little bit in the rest of this conversation because it does have a role to play in our parts count prediction. So let's go back to our ball bearing. It's a wonderful ball bearing right here. And we're going to try and come to terms with our preliminary understanding of how reliable this ball bearing is for our embryonic milling machine that we're going to make a lot of money off. So we know that virtually all ball bearings fail the same way. So for those who are veterans of my courses, it's got a teeny tiny bit of revision. But the point I'm trying to make is that we are very smart people and we know how our things fail. We know, for example, our ball bearings, believe it or not, comprise of these steel balls. A good chunk of the name comes from that word. Now, these balls touch what we call the inner ring, which rotates one way within the ball bearing. Wonderful component or device, a ball bearing. It's fantastically simple. Does a great job of allowing this inner ring to rotate with minimal friction. And because so many of our machines require rotation, shafts that turn, the ball bearings are one of the most prevalent little systems or components we see in the engineering world around us. Now, the inner ring, I should say, has a groove called the inner race, and that's where those balls roll along. And we're trying to create this rolling motion because rolling motion minimizes friction. That's why we have wheels on vehicles. Our vehicles aren't sleds that are not somehow propelled along a road surface where the bottom of the vehicle just skids along the tarmac. No, wheels and the rolling motion are a great way of minimizing friction. And so, of course, then we need to have these balls contained by the outer ring, which is usually where the ball bearing is physically held in place, and the inner groove on the outer ring is called the outer race. And so now we have the ability to hold the inner ring in a fixed location with respect to the outer ring, while the inner ring can rotate freely with minimal friction. And that's what the ball bearings as a little component does. Now, we don't want those balls to touch each other because that means you'll have the friction against those balls as they rub up against each other. So we often have a cage which separates those balls from another. And so now you have a pretty good understanding of how a ball bearing is constructed. Now, when I tried to explain the whole idea of the rolling motion, have a look at this little animation here. You can see how we have 6 balls. We have a cross section of the balls, and that red dot is just rotating, or as the ball rolls along and around. You can see the outer race is held still, but the inner race is rotating, and so the outer ring through those steel balls allows the inner ring to be held in place, and this rolling motion really does a great job of minimizing friction. And so that's all ball bearings do, minimize friction. So when I say that's all they do, it's actually kind of a big deal. I'm not trying to downplay the minimization of friction, but the ball bearing itself is a wonderful, wonderful device. Now, if we zoom in to the ball at the very bottom, which is often where a lot of the forces are being transmitted, let's have a look at what's going on down here. And again, like I said, it's a bit of revision, and there's a reason why it's going through this failure mechanism in great detail, because we really need to understand how our things fail in order to use these reliability parts count predictions. So you can see that this steel ball makes contact with the inner and outer race, and as it rotates. And in fact, we can zoom in a little bit more to really look at what's going along with that surface between the steel ball and in this case, the outer race. And so I'm not going to go through the failure mechanism in great detail, but I do need to go through it enough for us to understand how this ball, which rolls along machined but still imperfect race surface, will eventually cause our ball bearing to fail. And so as our balls roll along, you can see that we have this direction of roll represented by that arrow, which creates, and as it rolls across, it creates compressive force and a smaller friction force. When I say that ball bearings eliminate friction, that's not true. They minimize it. So there's a very large compressive force, which is how the outer race essentially holds the inner race in a fixed location. But there's a very small friction force. You can't eliminate all the friction associated with one thing rolling across another. So as the steel ball repeatedly rolls across the surface, the very first thing that's going to happen is that very large compression force is going to, which obviously is applied cyclically, is going to smooth out that outer race surface. And you can see then after we have that smoothing out, we have this hard inclusion, which is an imperfection. Everything's going to have an imperfection eventually, essentially. No matter how well we produce a ball bearing, it's going to have some sort of imperfection with its metallic lattice. And essentially an imperfection or a surface crack or whatever's going to happen, it's going to, as our steel ball starts to smooth the outer race, these compression forces are going to create these little cracks, these tiny cracks, which then are going to be subjected to cyclic tensile stresses, and that will cause fatigue cracks to grow, tensile fatigue. Essentially, a crack will eventually reach the surface, but then that friction force comes into play, and it's now going to essentially pull on one side of that crack, and we have what's called shear fatigue crack growth at an angle of about 35 degrees below the surface until the crack gets deep enough, it sort of turns left and starts paralleling the surface of the race. And then essentially once that friction force has enough surface area, it starts pulling away to the extent that the crack then turns towards the surface, and now we have a spalled pit. So why is this important? This is the first point where the ball bearing detects a signature of failure. So when we have our first spalled pit in one of our races, our ball bearing is still working perfectly fine. But we can now listen to our ball bearing and realize that failure is about to happen, because even though the ball bearing works fine, this spalled pit now becomes the focus of ongoing crack propagation and flaking, and essentially grows and grows and grows. It will eventually violently vibrate, create a lot of noise, heat, decrease in lubrication, and potentially could explode as the temperature of our ball bearing gets to the point where it essentially flies off the shaft it's associated with. So for ball bearings, virtually all ball bearings fail in the same way, this spalling mechanism. The main takeaway, or two main takeaways are, ball bearings wear out. As they get older, they become increasingly likely to fail. That's a degradation failure mechanism, accrual of damage. And if we want to, we can listen through vibration sensor or vibration monitor, part of a condition-based monitoring, a predictive maintenance regime, where we can have some form of early warning as it relates to ball bearing failure. So let's use this knowledge to understand how this relates to the random nature of failure of our ball bearing. So here are our 1,000 times to failure for a ball bearing that we are considering for our milling machine. Now, one maintenance strategy or management strategy for our ball bearing is to design it in a way such that we essentially run that ball bearing to failure. That's okay in some cases. The many components we don't swap out. On our vehicles, there's plenty of components and plenty of parts that are still going to be attached to that vehicle when we essentially trade it in for the last time. So a maintenance strategy of running to failure is of itself not a bad one if it aligns with your objectives and goals for your product, your system, your plan, or whatever it is. So if we have a maintenance strategy where you run that ball bearing to failure, then each one of those blue dots represents a ball bearing failure, which we will then remedy by replacing with a brand new one. Put it back in and off we go. So that's maintenance strategy number one. Maintenance strategy number two is a preventive maintenance regime, where as opposed to waiting for our ball bearing to fail before we do something about it, we try to understand its nature of failure and say, let's swap them all out at a fixed interval to prevent that really high failure rate associated with old ball bearings. Classic wear out failure mechanisms, the older they get, the more likely they are to fail, which means that we can often get a really good outcome from swapping out ball bearings or anything that wears out before they fail. So when should we swap out our ball bearings? There's the mean time, the mean cycles to failure, that balance point there. Well, let's select the preventive maintenance interval to be about 10% of the MTBF. And that might sound like a shockingly low figure, but realistically, this is in the conversation for a typical preventive maintenance interval. It needs to be relatively short with respect to some of the more well-known time to failure metrics like the mean. But the idea is that you want to swap out ball bearings before that large hump of failure madness starts to kick in. So let's just say this is a potential maintenance strategy number two, where we swap out our ball bearings at around 10% of their mean cycles to failure. That's number two. Now, number three is that we don't wait for a fixed interval. We are more proactive. So maintenance strategy number three is predictive maintenance that monitors the vibration the way I was telling you about. And so instead of just having a fixed interval, we measure the vibration of our ball bearing. And you can see here, this little vibration profile, we can tell when a defect such as spalled pit has started to create detectable vibration. Excuse me. And that means we might have some early warning of when that ball bearing is going to fail. So let's just say, for sake of argument, that we are able to detect spalling in our ball bearing at 95% of that ball bearing's time to failure. So we can see there's a huge spread of when those ball bearings are going to fail. And if we have, if we can measure the vibration, let's assume, for sake of argument, that for every ball bearing, we swap them out at 95% of the eventual time to failure, just for argument's sake. So that's just our, to create a point of difference to the previous two maintenance strategies. So now we have three maintenance strategies, which are obviously very different and are going to influence the failure rate of our ball bearing. So what does it, why am I torturing you with this this nonsense? Well, we go back to our ball bearing. We know ball bearings are really good at minimizing friction. And we're going to put this ball bearing into this mount within our milling machine. Now we know that if we have, for example, a failure rate given to us, we might be able to tell that for the ball bearing in question, the one we just looked at, the actual ball bearing we got from manufacturer A, the manufacturer might be able to tell us what the failure rate is for that particular ball bearing. Now, let's just say the manufacturer tells us that this ball bearing, I should say, has a nominal failure rate of 1.1077 failures per million cycles. Now, if for this ball bearing, we have that maintenance strategy number one, where we run it to failure, then we can perhaps start to understand the nature of, of this ball bearing reliability. So we know also, just for those people who are unaware of this little trick, this little equation, the MTBF is 1 over the failure rate. Well, actually, that's not really doing a good job of selling that one, because the MTBF is actually equal to 1 over the average failure rate. A lot of people forget about that. The average failure rate of our ball bearing. Why do we have to talk about the average failure rate? Well, the failure rate of our ball bearing is going to change over time. When it's brand new, when it's got no damage, the failure rate is going to be very low. But as it gets older and accumulates damage, the failure rate increases. So the MTBF has to be 1 over the average failure rate of ball bearings from go to woe. And in this case, for this ball bearing from manufacturer A, this implies an MTBF of 0.9027 million cycles between failures, or about 902,700 cycles between failures. Okay, so this is the MTBF for this ball bearing. Now you can see on top of our mount, we have that lubricant nipple. This is one of the things that we need to be aware of if we're trying to make sure that this ball bearing is going to last as long as the manufacturer says it's going to last. And if we don't do a good job of looking after our ball bearing, we don't lubricate it, or we put the wrong lubricant in, then we're not going to get the advertised failure rate. We're going to get a failure rate which is a bit higher. So in this case, if we don't look after our ball bearing, which is advertised with a failure rate of 1.1077 failures per million cycles, well, now it's got a much higher failure rate because we're not looking after it. Same ball bearing, which should have the same reliability characteristics, but if we don't look after it, after something, then it's going to fail more often. So you can't just simply look at a number from the internet, from a manufacturer, and say, well, that's exactly how it's going to perform in the field, because the good chunk of how that ball bearing fails is on you. That's why I went through all those factors where lubricant contamination, if you might recall, or particle contamination was the biggest factor which drove ball bearing failure. But of course, we're not going to be either of these two organisations where they let our ball bearing run to failure. Maybe we want to do preventive maintenance the way we described before. Preventive maintenance where we swap out our ball bearings at about 1/10 of the MTBF, which means we're going to replace after every 90,720 cycles, 10% of the MTBF. And if we do that, remember the failure rate was a little bit over 1 per million cycles. Some ball bearings will still fail before we swap them out. We can't ever stop failure from occurring outright, but we are able to prevent most failures before wear out occurs. And that means we now have much fewer failures. So when we have preventive maintenance, the failure rate goes from 1.1 failures per million cycles down to 0.2997. So we've improved reliability, or we've improved, I should say, the frequency of failures by 73%. When I say improved it, we've reduced it. But there's a cost, because when we do preventive maintenance, by definition, we are throwing out bearings which still work. And if we do the math, we are going to replace at a rate of about 11.1978 ball bearings per million cycles. And so even though we have much fewer apparent failures compared to the scenario where we run our ball bearings to failure, we're actually having fewer failures, but going through a lot more ball bearings when it comes to our preventive maintenance. So we're going through about 10.11 times as many ball bearings, but at the same time reducing failure frequency by about 73%. So that's preventive maintenance. Then we have that predictive maintenance we talked about. Wonderful approach if we can pull it off. And remember, if we're able to, for example, install a vibration sensor, let's assume we can, virtually every ball bearing there is, we can work out when the ball bearing has consumed 95% of its useful life. And for those condition monitoring people out there, I know this is an oversimplification. I'm not trying to suggest it's that straightforward, but just to look at the statistics, let's assume that we're able to swap out every ball bearing about 5%, or about 95% of its useful life, which means that we're going to replace at a rate of 1.1662 ball bearings per million cycles. So we're going to go through about 5.5% more ball bearings when compared to run to failure, but we have next to no failures as a result, because we're preventing the overwhelming majority of them using an understanding of physics. So what does that mean? That means for an identical ball bearing, depending on how it's used, depending on how you look after it, you can have seemingly wildly different failure rates, and more importantly, parts counts. So you can see on the left-hand side, we have, for the 4 scenarios we went through, the different apparent failure rates. On the right-hand side, we have different parts counts, and you can see the failure rate and parts count aren't always the same. If you're doing preventive maintenance, you're going to essentially throw out some potentially very good ball bearings. And that's a big problem, because when it comes time to compiling these wonderful failure rate tables on the internet and everything else, which number is being used? Is it the parts count? Is it the failure rate? Remember, you might recall in that little table I showed at the very start, there was one data source where the organization that gave that data had not observed a single ball bearing failure for, I think, about 800,000 cycles. How do we know that that is not a ball bearing which has an MTBF about 100,000 cycles, but that organization has a red hot vibration monitoring regime where it virtually allows no ball bearing to fail, but it's gone through plenty to create that overall duration of 800,000 cycles? How do we know that's not the case? The answer is we don't. And so even if you do get accurate failure data from these documents, you can see that depending on your preventive or predictive maintenance regime, the parts count is going to go through the roof. Now, this is one of the issues with reliability tables and parts count predictions, is that no one really talks about the fact that the failure rate and parts count can be very, very different. The preventive maintenance regime reduces failures by 73%, but we go through about 10 times more bearings. That might sound counterintuitive until you understand the statistics. And so you need to understand the maintenance strategy used by the organizations who provide the data to understand where the numbers come from, and we simply don't. So just be aware that this is a problem. And more importantly, perhaps, what maintenance strategy are you going to use for your ball bearings? That's a problem. If you don't know how those data points came to be derived in the first place, they might not have anything to do with how you intend to use your ball bearings. But of course, that's just one part or one issue with the parts count reliability prediction. Let's look at another scenario where we're going back to my wonderful smart lock, which I use a lot, and we're going to try and understand at the embryonic stage how reliable this smart lock is going to be. And of course, one of the things that we need to understand with our smart lock is how frequently that electric motor might break down. You could argue this is the most important component of our smart lock. And so if we pull it apart, we can see that there's a bunch of windings and there's a bearing and everything else. So let's just say at the very embryonic stage, we want to jump on that website that has those reliability tables, and we don't want to try and find some indicative way of characterizing the reliability of our little motor. Now, here is an excerpt from Mill Handbook 217, that's a very well-known source of those tabled reliability values. On the right-hand side, you can see a bunch of equations and a chart. Now, in this case, that chart there has temperature on the vertical axis and time on the horizontal axis. And what this chart is asking you to do is to try and characterize a temperature profile of the windings and bearings in your electric motor. You can see H1 represents number of hours spent in interval 1, T1, T2, T3, they're all temperatures. And the reason why you want to do this is because there's this wonderful equation which relates the different essentially cycles to failure for these different regions of this temperature profile. But here's the thing, this seems very robust. It seems like a very technical, theoretical, analytically robust way of coming up or understanding how your thing fails. But this equation is what we call a rule. And now rule sounds rather authoritative, and it's not really in the world of the engineer, I should say, because it's not in a textbook, it's never been proven, and it's not based on physics. So when we have something which is essentially someone's guess at how A relates to B, we call it a rule. But it's often presented in these books as if it's the truth. And it's simply not. And if you go through the process of coming up with a temperature profile for your electric motor, and you come up with the numbers and everything else, it creates this facade of robustness. This seems rather in depth. It seems like rather a detailed investment into understanding your your electric motor, but it's not. And it gives you a number which you might think is really, really accurate. It's simply not, because it's based on a rule. Then there's this thing called steady state, because people say, well, we're not interested in wear out and all that other stuff that you bang on about. We're interested in the steady state region of our components. We're not interested in how they're going to die, essentially. But here's a problem with that. Let's go back to Mill Handbook 217. The reason why is because if we look for the diode, one of the diodes, I should say, it has a baseline failure rate in this Mill Handbook 217 of 0.0038 failures per million hours. Now, that's very low, and diodes are really robust. We know how to make them pretty well, yeah, so we should have pretty low failure rates for electronic components. Problem with that failure rate is that implies an MTBF of 30,000 years, or more than 30,000 years. And why is that the case? Why do we have this clearly insane number in one of these textbooks, or not textbooks, but parts count prediction tables? The reason is that even though we know that diodes eventually wear out, it's all about where that data comes from. Now, that probability density function right there, that bell curve, represents how electronic components tend to fail. They tend to work very well until the heat and the voltage creates enough issues in the silicon lattice to create defects, which then trigger all sorts of other failure mechanisms. And once that happens, they wear out really quick. And so you have this really low hazard or failure rate at the very start. But most of the data for diodes and electronic components comes from this beautiful, young, just out of the oven, so to speak, diode, without it actually helping you work out how long your diode's going to actually last. So if you're happy using MTBS, where it implies that your components are going to last 30,000 years or more, you do as much research as you want. You use Mill Handbook 217 as much as you want. But you and I both know that capacitors have not, as an invention, been around for 30,000 years. Some would argue humans who invent capacitors have not been around for 30,000 years. It's just insane to suggest that these numbers are based on actual real-world scenarios where you're not interested in a failure rate where the capacitor is perfect and brand new. Things don't fail when they're perfect. They fail once they've accrued damage, and that's one of the biggest issues. You have these single numbers which represent this thing called steady state. And then there's environmental factors. Why is there environmental factors? Well, here's another table from Mill Handbook 217 where each one of these rows represents a different way of applying temperature, humidity, military operational scenarios, everything else. And so you have all these failure rates that or adjustment factors, which again have this facade of robustness, but no one knows where they come from. And even if they were right, Mill Handbook 217 is so old that they are based on components which we just simply don't manufacture anymore. Again, if you want to suggest maybe your capacitor is going to be used in a very humid environment, maybe its MTBF drops from 30,000 years to just 10,000 years. It's not a meaningful or appreciable change, and it still doesn't relate to how your things fail. There is no such thing as a rule as a constant hazard rate. There's no such thing as that steady state apart from that certain scenarios we see in textbooks. So let's go back to the statistical signature of our ball bearing, compare it to the statistical signature of something that wears in, like a small satellite, which in a very serendipitous way relies on a lot of those capacitors, which allegedly have a 30,000 year MTBF. And these, and when I say small satellites, again, really small satellites, you might notice that the balance point hasn't changed. The MTBF, the MTTF for both these devices, the small satellite and the ball bearing, is exactly the same, even though you can see that the PDF for the small satellite is hugging that vertical axis, which just goes to show how many small satellites fail very early because they have pre-existing defects or issues from launch. It's okay, that's how they fail. And so these different PDF curves, probability density curves, bell shapes, skewed bell shapes, infant mortality, you can see here are the different hazard rates which represent how much damage each device has as it gets older. For our small satellites, the damage appears to decrease, not because of magic, because the ones with the biggest defects fail early. And so the older a small satellite gets, the less likely it is to have a defect. And so even though we have the same MTBF, we have very different reliability characteristics. You cannot use a single number to characterize the reliability of different things. You just cannot do that. The data, like I said, is usually decades old and very limited. If your organization doesn't give up your reliability data for free, you better believe that every other organization has similar ideas. So who knows where this information comes from? It gives you also that false sense of accuracy. And the reason being is if you see a failure rate of 1.2967 failures per million hours, that seems precise. It's got 4 decimal points after that one followed by that period. But it could be based on, in many cases, one failure point. And so you get a lot of advice about how to use these numbers. Many people say plus or minus an order of magnitude at least. Again, it will also depend on how you look after your thing as well. Doesn't take into consideration different manufacturing quality. We know that if you buy the cheapest, nastiest ball bearing there is, it's going to have more manufacturing defects than the perhaps more expensive ball bearing that's manufactured properly from supplier B. So those parts count prediction tables, those reliability tables, don't take that into consideration. Doesn't take into consideration how you maintain your things. And I would argue that maintenance is perhaps the most important thing for the reliability of many systems and components, including ball bearings. We have no component that truly lasts, on average, more than 30,000 years, but many of these tables will suggest there are, not just one or two, lots. But there are, and so like I said, if you're happy with trying to tell your boss that your thing is going to last through till perhaps the next species of human evolves, that's fantastic. Use these tables. If you want to understand the actual reliability of your product, you can't use them. It's easier to pull numbers from these tables than do things like analyze, research, or test. That's one of the allures of these tables. One of the beauties of these tables is that you can essentially do a Google search, put numbers in a spreadsheet and say, there you go, boss, I've done the reliability analysis. And the boss won't know where you got those numbers from. It's certainly a lot faster than doing it through testing or researching or analyzing. And that's why there's an industry for these tables. You can also outsource accountability. What do I mean by that? Well, systems engineers love traceability. So when you have a systems engineering framework, often people value being able to say the source of that number more than actually using expert judgment. And so you might have a number in your gut, which you know is relatively accurate for the ball bearings you're about to use. But you can't reference my gut feeling or my instinct in a report in many environments. However, if you reference Mill Handbook 217, that seems very robust, seems very reliable. Why would the military put a handbook out there which is inaccurate? Therefore, you have some sort of traceability, which means that organizations will often value a document in the far rightmost column of the spreadsheet more than your best guess. And best guesses are pretty good when it comes down to it, especially if you know what you're talking about. They also, these tables I'm talking about don't tell you how your components or products fail, and they don't tell you how to maintain or improve reliability. You can only do preventive and predictive maintenance if your thing is wearing out. But as we saw, the MTBF can be exactly the same for another component which only wears in. Preventive maintenance won't work for that component. You need to address it in a different way. So perhaps the most important issue with these numbers is once those numbers get into your report or into your spreadsheet, they are almost impossible to get out. So I've seen many organizations say, well, we'll just use Mill Handbook 217, or we'll use publicly available mill reliability prediction tables or parts count reliability modeling tables. We'll just use the numbers in that report or in that table in our model until we get our own. Never once seen that work. Once those numbers are in a column in a spreadsheet or in a table, they never change because that work has already been done. You essentially remove the motivation from people to find numbers if they already have a number in there. And so it's borderline impossible to get these numbers out of spreadsheets and tables once they're in there. So if you designed your awesome new milling machine and you've got all these failure rates, which make it look like a very robust reliability analysis, no one is going to come back and say, okay, let's do this properly. No one. So be very careful if you're going to use those. Now, I have been bad-mouthing, so to speak, these parts count prediction tables and reliability failure rate tables for a good chunk of this conversation. And that's not the intent. I badmouth organizations which use those numbers without trying to understand the context. I badmouth organizations who are lazy, who just want to find a number to put in that table to say that that task is done. Because these failure rates can be helpful if you're trying to do some basic trade-off studies or basic comparisons between technologies at the very start of the production process. They can be useful if you're trying to work out if you should have a mechatronic design versus a simply mechanical one. Who knows which one's more reliable, and you do need to understand it yourself, but maybe you can use these failure rates to sort of come up with a vague idea about the reliability challenges associated with one technology over another. But like I said, I often see organizations which, when they get those numbers into their document matrix, they're almost impossible to get out. So that's where I'm going to call it quits for today. As per usual, had a couple of technical issues at my end. Are there any questions before we call it quits for October? Let me try and get my, excuse me for 1 second, my chat window has gone up to my teleprompter, so I just need to come in and see where my chat is. Very, very amateurish of me, I know. All right, I think I found it. So now I need to move it over there. All right. I just got one message from Carl. Thanks, Carl. Any questions? Oh, I got a Q&A over here. All right, got 5 open questions, all from Carl. Okay. So Carl writes, ball bearings are great because they reduce friction, making machines more efficient, can handle both radial and axial loads. Their low friction design is ideal for high-speed applications. And versatility allows them to be used in a wide range of products from small electronics to large machinery. Agreed? Question mark? Yes, I agree. What else do you say, Carl? For optimal performance, the ideal number of ball bearings is a compromise between load capacity, speed, and cost, rather than simply fewer or more. So, of course, you're talking about trying to optimize some of the design characteristics of ball bearings, which is always a thing. Advantages of deep groove ball bearings over other bearing types. Any thoughts? So that's a whole new conversation. And to be honest, there's ball bearing experts out there who know more about this than I do. But one of the reasons you want to have deep groove ball bearings is because it can help minimize or help deal with axial loads, thrust where the rotating shaft is going to and fro axially. So if you have scenarios where you need to deal with that, deep groove ball bearings might be the way to go. You'll have a higher friction cost as a result, but they will be able to handle those axial loads better. So it depends on your scenario. Reliability data is crucial for organizations as it builds trust, improves decision-making, increases efficiency. Accurate and complete data leads to better marketing, more accurate forecast, enhanced operational efficiency, and the ability to meet regulatory compliance. Without reliable data, companies risk costly errors, missed opportunities, and a weakened competitive position. Agreed? To a point, you're just not going to get the failure data you need to understand the warranty period reliability of some products. You simply cannot test products for 2 years if that's your warranty period. So you can never have truly complete data in the way some people say it, some people view it, and that you have truly representative data from how the users actually use a thing. You need to use gather data very judiciously because it can be expensive, because you gather data through testing, or you gather data from paying someone to analyze your system. And you really want to make sure you focus on the vital few. Richard Denning writes, instruction not to use 217 was issued 20 plus years ago by the Assistant Secretary of the US Army. Yes, I forgot to mention that. Even though Mill Handbook 217 is still widely referenced in contracts, including those from the DoD, and is widely referenced in many organisations who sell parts count prediction reliability tables. Right. Mahendra writes a question. Here we go. To recap, you correctly parts counts can be used for design comparisons on a relative basis, but not an absolute basis. For example, it can be used for comparing PCBA designs between old and new generations to check if the new gen PCA is at least as good as the previous one. I would agree with that up until a point. And the reason why I say that, if you have data from previous generations of a PCB or a PCB assembly, you should know what the weak points of that PCB are. You know if you're getting a lot of fatigue cracking around the solder joint next to that large capacitor, or if you're having a resistor, which is not a surface mount resistor and it's getting fried a lot, or you don't have ESD protection. So in terms, if you have a legacy device or a legacy component, I'd suggest you really need to understand how that thing has failed, because that will give you data, or you should have data if it's legacy. And that means that you can do all sorts of wonderful things like design your next generation to be more reliable. So comparing legacy with new generations, I wouldn't suggest these handbooks be quite as useful. But if you're trying to design something from scratch and you're, for example, trying to compare a purely mechanical subsystem with a mechatronic subsystem, with a CNC subsystem, perhaps those subsystems, different technologies are fundamentally doing the same thing. They all have their pros and cons. You want to get a general idea of which one will be more reliable than the other, then yes, you can use those tables up until a point. But once you start understanding the physics of how your thing fails, you really should be focusing on designing out that fatigue crack initiating point on the door handle, or adding an additional mount on that PCB to minimize vibration. Carl writes, any thoughts about air bearings? Well, lots of thoughts, but again, I don't want to steal the thunder of people who deal with air bearings way more than I do. When it comes to air bearings, as it relates to this conversation, I do not think there's a lot of failure data in Mill Handbook 217 or comparable documents. So I'm not entirely sure about what off-the-shelf numbers you can find for air bearings. And again, air bearings are just like anything else. They cannot essentially have the same, you don't get to have the same amount of load that they can support. But by the same time, if you do have air bearings, if you have small loads, you can have extraordinarily low frictions. Any more? We might be done, Fred, unless I missed one.
Yeah, there's one from Richard Denning in the chat. Instructions not to use 217 was issued 20 plus years ago by Assistant Secretary of the US Army, and he has a link to it.
So what was that one, Fred?
The Richard Denning put a post saying, or a comment, instructions not to use 217 was issued 20 plus years ago by the Assistant Secretary of the US Army, and has a link.
Yes.
Despite that, it's used every day.
Yes, right.
All right, think that's it.
All right, team. Second last one for the year for me. So I'll see you next month for those who want to returns for my monthly diatribes November. But hey, thank you for your attendance. Any questions, feel free to reach out. Again, I'm not bad mouthing the table, I'm just bad mouthing how they're used.